Okay, hello everybody. Last time we discussed the solution to the problem about the block on the slope. So we had a block on the slope, and the slope angle was alpha with the horizontal, and we considered the acceleration of the slope, which can be directed only along the slope, parallel to the slope. And the acceleration of this body m was due to two forces. One force was the component of the body weight, component parallel to the surface. And another force was the force of friction. And you remember that the force R was equal to mg sine alpha, and the force F was equal to mg k cosine alpha. And the second Newton's law gives the product of mass times acceleration must be equal to the total force or resulting force acting on the body along this axis parallel to the slope. So that will be R minus F, and that will be mg sine alpha minus k cosine alpha. So that the acceleration of the block equals g sine alpha minus k cosine alpha, where k is the coefficient of friction. We obtained this result last time, and we noticed this interesting thing that if angle alpha is small, so in case alpha tends to 0, then sine alpha will tend to 0, and the first term will vanish here. And the second term will be equal to minus k, because cosine alpha for small alpha tends to unity. So the total acceleration will be minus kg, approximately, in this limit, which is certainly not correct. This is incorrect because we never observe objects accelerate when they are on a flat surface. The angle of inclination is 0 or very small. That is the inclined surface, the slope, with small angle, and the bodies here does not accelerate. We can increase the angle, it does not accelerate. And it does not accelerate when the angle is 0, when the surface is horizontal. But the formula gives you some acceleration, which is absurd. So this is the case when the formula predicts the result which does not coincide with what we observe. The observation is in contradiction with the formula, or the formula is in contradiction with observations. How can we deal with such a situation? That's a very interesting situation, and I underline this simple case in order to show you how to deal with such case when the formula is in contradiction with observations. Sometimes it happens in physics. Sometimes it happens in mathematics also. Sometimes it happens. What does it mean? There are several possibilities. First, the formula may be incorrect. We may have done a mistake somewhere. But this is not the case here, because the major law of physics is the Newton's second law of mechanics, which is correct. In our classical physics, in our laboratory, on the surface of this planet, the second law, Newton's second law, holds and is very good and very precise and predicts all the mechanical processes with high accuracy. So the formula is good, it's correct, and the calculations are so simple that there is no place to make a mistake. So we made no mistake. But anyway, we obtained the result which is in contradiction with observations. In this case, we have to analyze this result and this formula. What do we observe? And we have to start from what we observe. If we start from mathematics, we obtain absurd result. So let us start from what we observe. We observe a body which is on horizontal surface. Alpha is 0, and there is no acceleration. The body does not accelerate. So acceleration is 0. This is for certain, because we can see it, we observe it. Acceleration is 0 in our particular case. That is the result of observation, and we have to take it into account. We have to take it for granted. If a body is on horizontal surface, it does not move. Acceleration is 0. Okay. Let's substitute 0 here for acceleration. If here is 0, g will cancel, and we will obtain that sine alpha will equal to k cosine alpha. And from here we obtain that k equals sine alpha divided by cosine alpha, which is by definition tangent alpha. So, if we start from what we observe, if we start from experimental results, we inevitably come to this conclusion that k is actually a function of angle alpha. K is not constant. K depends on the angle alpha. So we come to conclusion from the observations. We come to this conclusion that k is some function of alpha. It's not a constant coefficient. We assumed originally that k was constant, but actually it turns out that k must be a function of alpha. If so, if this is true, then there will be no contradiction with our formula, because if alpha is 0, tangent alpha is 0, then k is also 0. And if you substitute 0 here, you will obtain 0 acceleration, just what we observe. So if we start from observation, we will obtain no contradiction at all. The formula will predict exactly what we observe. But the coefficient k will be, in this time, it will be a function of angle. So if the angle is small, or 0, the coefficient of friction is 0. But if we increase the angle, the coefficient of friction will increase as tangent alpha. Here is angle alpha. And when we increase alpha, the coefficient of friction increases. And all the time, the coefficient of friction is such that the acceleration is 0. It means that r equals f. The force r is equal to the force f. Always, whenever the body is at rest, whenever there is no acceleration, then all the forces acting on the body compensate each other, or cancel each other, or balance. People say the forces balance each other. So there is no acceleration, because the force tending to pull the body downward equals the force of friction, which is directed in, which has opposite direction. So these two forces cancel each other. And only if alpha is larger than some critical value, then the body starts sliding down. After alpha is larger than some critical value. So if we draw a graph of alpha, coefficient of friction k as a function of alpha, then we must take into account that coefficient of friction is a function of alpha. And what is this function? This is tangent. And we know how tangent, what is this function tangent? That's it. And it will go to infinity when alpha is pi over 2 at this particular point. The tangent alpha will go to infinity, but the coefficient of friction will not go to infinity. It will increase as a tangent with alpha, and at some critical alpha 0, the coefficient of friction stops increasing. And then if we increase alpha further, the coefficient of friction will remain constant in this interval of angles alpha. The coefficient of friction will remain constant. And when it's constant, then the force R will become larger than F. And if force R is larger than F, then the vector sum of these two forces will be non-zero. And if R is larger than F, then R minus F will be not zero, will be some positive value, and so we will obtain some acceleration, non-zero acceleration at this particular angle. So non-zero acceleration will occur at a certain angle when the coefficient of friction stops growing. Here at smaller angles, the coefficient of friction grows, increases together with the angle. But after some critical angle, the coefficient of friction remains constant, and the body slides down with these coefficients of friction. Such is the analysis of this situation. If you don't do any analysis, if you don't analyze the situation, you will come to an absurd conclusion that there should be acceleration, some acceleration at zero angles, at small angles. But if we start from observations, we come to conclusion that coefficient of friction should increase with alpha for small alpha. And then after some critical alpha, it will remain constant, so that there will be some acceleration depending on angle alpha as dictated by this formula. The acceleration will depend on angle alpha if the first term is larger than the second term. Such is the analysis of this situation with the block on the slope. Any questions? Whenever a body is at rest on horizontal surface, there are no forces of friction actually, and coefficient of friction is 0, and the force of friction is 0, and there are only two forces acting on this body. Only two forces. Which forces? A force is the measure of interaction. So in order to find force, we must consider interactions. This body interacts with two objects in the outside world. First, it interacts with the planet Earth, and therefore there is a gravitational pull, a gravity pull directed downward to the center of the planet. This is one force. Due to this force, the body will fall down with acceleration of free fall. And another force is the reaction force of the surface. And if the body is at rest, these two forces balance each other. One force directed downward, another force directed upward, and they are equal in magnitude, and they balance each other. And therefore, the body is at rest, and no forces of friction are involved. When do you have a force of friction? Only when you try to push this object sideways. When I try to push it, then there will be a force of friction, and the coefficient, some coefficient of friction will come into play and will somehow provide the force of friction. So the force of friction is not a simple force. It's a complicated phenomenon. A force of friction is a complicated phenomenon. And the more you study forces of friction, the more complicated this phenomenon will seem to you. Because forces of friction are behind the sounds of violin, for example. Forces of friction can somehow be influenced by lubricants. If you use some oil to lubricate the surface, the friction will change. Forces of friction sometimes depend on the velocity of motion. If you have lubricant, or if you consider friction in the atmosphere, that there is air drag, this force of friction will depend on the velocity of the body. So forces of friction are not as simple as that. Actually, every phenomenon is not so simple as it may seem at first sight. Any phenomenon in physics is complicated, and if you study this phenomenon in depth, then you will discover more and more complications, more and more interesting things. That's the usual situation. Okay. After clarifying the coefficient of friction and what happens with it, we may consider a problem to demonstrate Newton's laws. Let's consider problem number 62. A bead of mass m is fitted onto a rod of length 2L and can move on it without friction. So we have a rod of length 2L, and there is a bead of mass m. At the initial moment, the bead is in the middle of the rod. So at the initial moment, the bead is here. And there is a hole in this bead that it can slide along the rod without friction. So at the initial moment, the bead is in the center. It means that this part of the rod from the bead to the end has length L, and another part is also of length L. The rod moves translationally in a horizontal plane with an acceleration a in a direction forming an angle alpha with the rod. So the rod is moving in this direction at angle alpha with acceleration a. The rod as a whole accelerates translationally. That is a translational motion. It means that in the process of motion, the rod remains parallel to itself, parallel to its former positions. That is, the angle of the rod orientation does not change. The rod is directed always at the same angle. And all this picture is in horizontal plane, as it's stated in the problem. The rod moves translationally in a horizontal plane. So this is a horizontal plane. Otherwise, the bead would simply slip off, and fall down at the end of the rod. But it doesn't slip, because this is horizontal rod and horizontal plane. Find the acceleration of the bead relative to the rod. So the bead will somehow be accelerated relative to the rod. Acceleration of the rod is given, and we have to find the acceleration of the bead relative to the rod. I put here letter R in this index R to underline that this is a relative acceleration, a bead accelerating not relative to the Earth, but this is an acceleration of this bead relative to the rod. And we must find the reaction force exerted by the rod on the bead. So there is some reaction force N exerted from the rod on this bead. And also we have to calculate the time interval after which the bead will leave the rod. The time interval tau, we have to find it, the time interval of bead motion after which the bead will leave the rod. So the rod moves here and the bead slides along the rod because the rod moves with acceleration A. It moves faster and faster. So the bead will slide along the rod and finally it will slip off the end of the rod. And we have to find the time of bead travel along the rod. Okay, let's discuss this situation with the bead and the rod. So, should the rod accelerate in this direction, then if there is no friction between the bead and the rod, then the bead will simply remain where it was. It will remain at rest because there are no forces of friction. And the rod accelerating here and the bead remaining at rest will result finally in the bead slipping off the rod when this end of the rod will be at this point. The bead will slip off and fall down. That is one situation. Another situation when the rod accelerates in perpendicular direction. So the bead is here and this is in horizontal plane. And if the rod accelerates in this way, then the bead will remain always in the center of this rod. It will not slip away from the center. If the rod as a whole accelerates in this direction, perpendicularly at the right angle to the rod, then it's obvious, we can understand it, we feel that will be true. This is our intuition, that in this case the bead will quickly slip off the rod, and in this case it will not slip along the rod. It will accelerate together with the rod. This is clear from intuitive point of view. But in our problem we have some intermediary case when the rod is accelerated at some arbitrary direction at angle alpha to the rod. How to analyze this situation? As the rod accelerates, there must be some force of interaction between the bead and the rod. When you are in an accelerated reference frame, for example, you are sitting in a car which is accelerating, what do you feel? You will feel that some force presses you back against the seat, against the back seat. So you will be pressed backward if the car is accelerating. This is the force of inertia, and the same force will act on the bead. Some force will move the bead somewhere. It will resist the acceleration. But what may be the direction of this force of interaction between the bead and the rod? What may be the direction? If this force is directed at some arbitrary angle, then the force of interaction between the bead and the rod, then there will be some force component directed along the rod. But this force component cannot be here because there is no friction. There is no friction between the bead and the rod. So this component must be zero because no friction. If there was some friction, then there could be such component, but there is no friction. So if this component must be zero, then the force F must inevitably be directed perpendicularly to the rod. And this force, by the way, we have to find it because the question is what this force is equal to. So by simple consideration, by simple analysis, we establish that this force is perpendicular, must be perpendicular to the rod. Why? Only because there is no friction between the bead and the rod. No friction. That is why this force, we don't know the magnitude of this force. We must find the magnitude. We must somehow calculate the magnitude of this force. But the direction of the force can be established easily. The force is directed perpendicularly to the rod. That is, from the very beginning, it's clear, because there is no force of friction between the bead and the rod. Okay, if the force acting on the bead from the rod has this direction, then the acceleration of this bead will also coincide with the direction of the force. That will be the acceleration of the bead relative to the Earth. So this is the acceleration of the bead. Let me denote it by AB. Acceleration of the bead relative to the Earth. That is not the acceleration of the bead relative to the rod, which we have to find in this problem. This is a different acceleration. We are here in the laboratory standing on the Earth, and we observe this rod accelerating and the force acting on the bead in this direction. Therefore, we should observe the acceleration of the bead in the same direction as the force. The force and acceleration will coincide because of the second Newton's law, which says that the force acting on the body equals its mass. Mass of the bead is given, times its acceleration relative to the Earth or relative to laboratory reference frame. That is in the inertial reference frame we discussed with you. I discussed already the inertial and non-inertial reference frames. So because of the Newton's second law, we know that if we obtained the direction of the force, then we know the direction of acceleration. We don't know the magnitude of acceleration, but we have already established its direction. Direction of acceleration of the bead relative to the Earth will be perpendicular, the vector which is perpendicular to the rod. And the rod itself is accelerating. That is the acceleration of the rod relative to the Earth. So if the bead accelerates in this direction, it means that the bead moves in this direction relative to the Earth. And the rod moves in this direction. The end of the rod, the point A, moves along this trajectory. And this point B moves in this trajectory. And so that after some time interval, the rod will be here, accelerating in this direction. The rod will take this position after some time interval, which we have already denoted as tau. because at this particular time moment, the bead will reach the end of the rod and will slip away from the rod. So this is the point when the bead leaves the rod, slips off the end of the rod. So we have some geometrical figure which shows the trajectory of the bead motion relative to the Earth, and the trajectory of point A motion, the end of the rod, again relative to the Earth. And we understand that when these two lines intersect at this particular point, the bead will slip off the rod, slip away, and will leave the rod. So that is something in the solution of this problem. That is very important observation, because we know that point A is accelerating at acceleration A. It means that the displacement of point A from position A to A prime, this displacement of point A, which can be denoted by S, due to well-known kinematics formula, can be expressed as A time interval squared over 2. And I put here time interval as tau, because I know that this is the time interval which is required for the bead to slip away from the rod. So alpha time squared, A acceleration time squared over 2, that is the displacement of the accelerating point. A accelerates, point A accelerates, and finally is found in position A prime. During the same time interval, the bead will accelerate and move along this trajectory from the initial point O to final point A prime. And this displacement of the bead can somehow be denoted by some letter, for example, L. And the displacement of the bead will be what? Acceleration of the bead with respect to the Earth, AB, the same time interval squared over 2. The bead covered this displacement, made this displacement, covered this length in the same time interval which is required for point A to go from initial position A to position A prime. And the same time interval will be required for the bead to go from the initial position O to its final position A prime. The time interval is the same, but accelerations are different, and S and L are different. And we know from geometrical considerations that L divided by S, that is this leg, opposite leg of the triangle, the leg opposite to angle alpha in the right triangle, divided by hypotenuse S, will give you a sine alpha. Opposite leg L divided by hypotenuse S will give you sine alpha. Alpha is given. Alpha is given. So substituting these formulas here into the last formula, we will obtain A tau squared over 2 divided by AB tau squared over 2, and all this is equal to sine alpha. Tau squared will cancel, 2 will cancel, and we obtain that sine alpha equals A, acceleration of the rod, divided by AB, which is acceleration of the bead relative to the Earth. From here, we can immediately find the acceleration of the bead relative to the Earth, which will be A, acceleration of the rod, which is given, divided by sine alpha. Actually, we don't need this acceleration AB. We need some other acceleration AR. But this is the first important step. We have found some acceleration of the bead relative to the Earth. Okay, maybe it will help us in finding the required quantity AR, which is acceleration of the bead relative to the rod. I hope so. Uh-huh.
Question.
Okay.
There we said L divided S is equal to sine angle alpha.
Uh-huh.
And then here we substituted them with their formula.
Yeah.
Like for the L is the acceleration of bead with time square over 2.
Yeah.
So I see here we've put the vice versa. Is it okay?
What?
Down here, there, from the, yes.
A divided by AB.
Yes, but we say the L is AB, acceleration of L. Yes, you see L.
L.
L is equal to acceleration of bead.
Yeah.
Okay.
So L, yes.
Yes, it's supposed to be on top of.
Yes, it should be in the denominator. Thank you. Thank you. That was a mistake, a typo. Sure. So, okay. So this fraction should be inversed. By the way, before you told me about this mistake, I looked at this formula and thought about one simple thing. What if alpha goes to 0? Then sine alpha will go to 0, and 0 in denominator will make this quantity infinitely large. So we will obtain infinitely large acceleration of the bead, and infinitely large acceleration will give infinitely large force. Something is wrong. That flashed in my mind. I just noticed that something was wrong, and you immediately told me what is wrong here. Okay, thank you. So this fraction should be inverted, AB divided by A. Otherwise, we obtain absurd result involving infinite accelerations of the bead at small alpha and infinite forces, which cannot be realized. So the correct answer will be A sine alpha. Okay. And if we know acceleration of the bead AB with respect to the Earth, then we know the force acting on the bead, which is necessary here to find in this problem. So the first question, what is the force of interaction between the bead and the rod? The first question is solved. We know that we have found the answer. The force should be acceleration of the bead times mass. So it will be the mass of the bead, A sine alpha. That is the answer to this question. That's it. One question answered. The answer to one question is found. I hope the answers to other questions will be found in the same way. Okay, let's have a 5-minute break. Okay. So actually the problem is as good as solved, because the remaining questions, the remaining quantities are very easy to find. For example, how can we find the time interval tau during which the bead will slide along the rod? We know we have found the acceleration of the bead AB with respect to the Earth. So we can use this formula to express tau as a function of AB and L. And L is not known, capital L is not known, but small l is given in the problem. And small l and capital L are connected in geometrical way. The relationship between them, the ratio of capital L to small l is tangent alpha. So capital L divided by small l is tangent alpha by definition. Therefore, capital L equals small l tangent alpha. We know this distance, capital L. And if we know this and know this one, then we can calculate tau. Tau, the time interval, will be given by square root of 2 capital L divided by AB. And this will give us square root. L is capital L is small l tangent alpha from here. And AB, acceleration of the bead with respect to the Earth, is known. It's acceleration A sine alpha. This is not the end of calculations, because tangent by definition is sine divided by cosine, and so sine will cancel here, and we will obtain square root of 2 small l divided by acceleration of the rod A cosine alpha. That is the time interval required for the bead to slip off the rod. You know why I don't like this formula? Try to guess why I don't like it. Something's not good here. Something's again, something's not good.
Cosine, if alpha goes to 90 degrees, then
Cosine will be unity, not a problem. But if acceleration of the rod is 0, which is quite possible, that is the rod, and it's at rest here with 0 acceleration, no problem. Then 0 acceleration will give you infinite time. Oh, that's okay, infinite time. It will never, the bead here will never slip off. It will remain on the rod forever if the acceleration is 0. Everything is okay. I thought that infinite is wrong, but no, it's good. Infinite time interval is quite reasonable. If acceleration of the rod is 0, the bead will never slip off the rod. So the time interval required to move to the end, to the point A, will be infinite. That's okay. That seems to be correct. So the longer the rod, if you increase the L, the larger will be the time required for the bead to slip off. So if you increase L, then the time will increase. That's good. If alpha goes to 0, then cosine is unity, and the formula will give you the acceleration, the time interval needed to go for the bead to go from the initial position to point A with acceleration A. That's okay, that's the same formula. But if alpha is 90 degrees, then cosine will be 0. And what is 90 degrees? It means that the rod accelerates perpendicularly, and in this case the bead will remain here forever. So if alpha is pi over 2 on 90 degrees, then cosine will be 0, and you will wait for infinite time until the bead slips off, and it will never slip off. So this formula is quite reasonable. It seems to be correct. Also, you may check this formula for units of measurement. Units of measurement of length is meters, and acceleration is meter per second squared. So meters will cancel here, and what remains second squared here. And after taking this second squared from this square root, you will obtain seconds. So this quantity is measured in seconds, which is absolutely necessary to have time interval. So the units of measurements are good, and physical sense also is good here. So we have found the time interval for the bead required for the bead to slip off. We have found this quantity. And the only remaining thing is to find acceleration of the bead relative to the rod, which is also very simple to find, because within the time interval tau, the bead will go from initial point O to its final point A relative to the rod. The bead will go from here, from the center to the end, and then slip off. So the distance is known, the distance L is known, and the time interval is known, and acceleration of the bead relative to the rod may easily be calculated if we use a similar formula, similar to what is written here. So the length or the distance covered by the bead is the acceleration of the bead relative the rod, that is AR, time interval squared over 2. Everything is known here except acceleration. So acceleration AR can be found as 2 small l divided by tau squared, and that will be 2l, and tau squared will be 2l a cosine alpha, 2l cosine alpha. 2l will cancel, and acceleration, which is needed, which is to be found here, acceleration will be given as acceleration of the bead relative to the rod will be equal to a, which is the acceleration of the rod, cosine alpha. That's it, the answer to the last question in this problem. Any questions? Actually, to solve this problem, we need only the formula connecting the distance covered by a uniformly accelerated body during some time interval t. Only this formula from kinematics is involved in this problem. Also the second Newton's law. And the major part of the problem is solved by geometrical considerations. So in order to solve this problem, first of all, you have to draw the sketch. You have to carefully draw the picture which shows all the processes in this figure. If you are good in drawing pictures, then it will help you a lot in solving problems in physics. It will help you a lot. The most important step in solution was this figure, which shows everything. The dependence between capital L and small l and S and alpha. That is the main thing, the core of solution. Next problem. Number 63. The next problem will be number 63. It says, solve the previous problem, that is number 62, which we have just considered, assuming that the moving bead is acted upon by a friction force. Now we have to take into account some friction between the bead and the rod. The coefficient of friction between the bead and the rod is K. Disregard the force of gravity. If it says disregard the force of gravity, it means that the rod is horizontal. Again, as in the first problem. The rod is horizontal. If you consider non-horizontal rod, something like that, the bead will slide down by itself without any acceleration of the rod. So the rod is horizontally placed, and the bead is here on the rod, and the rod is accelerated sideways at some angle. And we have to consider the same problem and taking into account the forces of friction between the bead and the rod. We already mentioned in our discussion that if you go to this accelerated frame of reference, which is a non-inertial reference frame connected to the rod, then in this non-inertial reference frame, anything sitting on this rod will experience the action of some force which is directed oppositely the acceleration of the body, the acceleration of the rod in the opposite direction, and that will be the force of inertia, the same force which is known to press the passengers of the car against the seat. When the car is accelerating forward, all the passengers are pressed in the backward direction. That is the force of inertia acting in the accelerated reference frame. So the rod is an accelerated reference frame, and there must be a force of inertia acting on everything connected to the rod, and there is only one thing here, that is the bead. The bead, there is some force of inertia. I will draw another sketch. So the force of inertia will be directed here oppositely the acceleration of the rod. And this force will act on the bead. And what will be this force equal to? The mass of the bead times acceleration, ma. The situation is very similar to that of the force of gravity. And if we draw this picture in such a way that the acceleration of the rod is directed upward, that is the rod, and the acceleration is directed here, and the bead is here, and the force of inertia is directed here, downward. Then, in such interpretation, we notice that this force of inertia is very similar to the force of gravity, with the only difference that the force of gravity is mg, where g is the acceleration of free fall. And here we, instead of acceleration of free fall, we have the acceleration of the rod, which is directed oppositely in this case. So if we notice this similarity between the force of gravity and the force of inertia, then this problem becomes absolutely equivalent to what we have considered in the beginning of the lecture, that is the body on the slope, where the only force acting, the major force acting, is the force of gravity, and also there is the force of interaction between the block and the surface, which is the force of normal reaction. So the same thing will be here, the force of gravity and the force of normal reaction directed here, and as the result of action of these two forces, the bead will accelerate here So these two forces must add to produce something like that. Well, the problem of the block on the slope was solved and discussed, and we know the solution, the acceleration, what is the acceleration, and we have even discussed this subtle thing related to the coefficient of friction, which sometimes can actually be 0. And so the actual coefficient of friction is between 0 and some maximum value which is given in the tables of physical quantities. So this is the maximum possible maximum value of coefficient of friction, this one. And actual coefficient of friction is between 0 and this maximum quantity. The same will be true here. And the acceleration of the bead relative to the rod, acceleration of the bead, this one, AR, acceleration of the bead relative to the rod, AR, will be given by this formula. And the only difference will be that instead of the acceleration of free fall, we must take the acceleration of the rod, A, which is given in the problem. And then we must be very careful about angle alpha. Here, alpha is the angle between the slope and the horizontal. And here, alpha is the angle between the rod and vertical. So alpha here is somewhat different from alpha there. What is the difference? If you take vertical direction and this angle like beta, then alpha plus beta will be 90 degrees. That will be the right angle. And so sine alpha will be cosine equal to cosine beta. So in this formula, the sine should be changed into cosine, and vice versa, cosine should be changed into sine, because alpha in this problem was meant to be this angle, and alpha in the last problem will be equal to this angle. The meaning of alpha is different. So here will be cosine alpha, this one, minus k sine alpha. That is, we have found the acceleration of the bead relative to the rod. How did we come to this formula? By analyzing the solution of the first problem considered today, that is the block on the slope. We just took we take the formula which was already derived earlier, and we used this formula, applied it to a new situation which is practically the same, with the only difference that we take acceleration A instead of g acceleration of free fall, and angle alpha is slightly different angle, this one instead of this one. Okay, after we obtain this solution, we may compare it with the solution previously obtained here. The acceleration was a cosine alpha when there was no friction. When coefficient of friction was 0, we obtained the solution, the answer, a cosine alpha. So if coefficient of friction is 0, the second term vanishes, and we obtain here the same expression, the same formula, a cosine alpha, coinciding with the previous solution. So I will not repeat all the same analysis. We have already discussed it in the previous problem, and this problem, which takes into account the coefficient of friction, can easily be now generalized if we have found the acceleration AR of the bead relative to the rod. Then we can repeat all the same logic to obtain all the answers to this problem if coefficient of friction is taken into account. Any questions? Is it clear? The analogy between acceleration and the forces of inertia and the forces of gravity. By the way, analysis of this very close connection between forces of inertia and forces of gravity. The analysis of this relationship between the two forces allowed Albert Einstein to obtain his general theory of relativity, which describes gravitation, which is the relativistic theory of gravitation. So the Einstein's theory of gravitation is based actually on this concept that the forces of inertia are somehow analogous to the forces of gravity. That is the basic concept which underlies the whole Einstein's theory. So this is very productive. I would like to consider another problem, which will be problem number 65. To illustrate the application of Newton's laws, a wagon with a mass m moves without friction over a horizontal rails at a speed v0. So I draw a picture immediately. A wagon or a railway car moves without friction at velocity v0, and the mass is given, the mass of this railway car is given. A body of small mass m is placed on the front edge of the wagon. So a body of small mass m is placed here. Well, I don't know, small, if the mass is small, it may not necessarily be small. Any mass denoted by small letter m. A body of mass m is placed on the front edge of the railway car. Here, it's placed here, without the initial velocity. So the car moves here at velocity v0, and the body is placed at this point without any initial velocity. The initial speed of this body is 0. Of small m. At what length of the wagon, or I would say a railway car, at what length, we must find this length L of the railway car, at what length will the body not slip off the railway car? Disregard the dimensions of the body. The dimensions are considered to be small as compared with the length of the railway car. The length is much larger than the dimensions of this body. And the coefficient of friction between the body and the surface of this railway car is given. It's k. Okay, let it be here k. The coefficient of friction is given. And we must find the length of the car such that the body will not slip off the car. It's obvious that if there is no friction, then the body will slip. The body, if placed here without the initial velocity, will slip along the surface and then fall down if there is no friction at all. The railway car will move in this direction and the body will slip and then fall down here at the same point. If there is some friction, the body will be accelerated together with the moving car. But if the length of the car is too small, then the body will slip and travel along the surface of the sky and then fall down. So we need to find such minimum length, or such length of the railway car, that is the length L of the railway car, which is required for this body not to slip off the car. Is it clear? The question is clear?
Can you repeat again?
We must find such a length of the railway car from this point to this point, which is enough for the small body to remain on the surface of this railway car. If you take smaller length L, then the body will slip. But if you take larger length, then the body will remain on the surface. It will not slip. We must find such a length of this railway car. So the first step in solving any problem, the first step is what? Make sure that you understand the statement of the problem. That is the first step. So if you don't understand, if something is unclear to you, you must read the statement of the problem again and again and draw a sketch and draw all sorts of pictures to illustrate what's going on in order to understand fully all the processes which take place here. The first step is always, whatever problem you solve in physics, in chemistry, in mathematics, in whatever science, any problem can never be solved if you don't understand the statement of the problem. So first step in solution is to understand the statement. That's why I ask you if it's clear, if everything is clear. Okay?
So you say that the body will slip at the other direction.
Yes.
The direction of the motion.
Actually, the railway car moves in this direction, and the force of friction acting on the body will have this direction. Let it be force of friction F. Right? So this body, if acted upon by this force, will accelerate in the same direction. But if the force is small, the acceleration will be small, and the body will move slowly with small acceleration. And the railway car, which moves quickly, will move into this new position, while the body will not be able to go as fast as necessary in order to remain on the surface, and the body will slip off the opposite end of the car. That is. Okay? What do we have here? The body had initially zero velocity, but the force of friction is acting on it, so it will be accelerating. According to the third Newton's law, the same force will be applied, the same force of friction will be applied to the railway car. And so the railway car will decelerate under this force of friction. The force of action is equal and oppositely directed to the force of reaction, according to the third Newton's law. See, these two forces are equal and oppositely directed and applied to different bodies. This force of friction is applied to a small body, and this force of friction is applied to the railway car. So the first force of friction will accelerate the small body, and the second force of friction applied to the car will decelerate it. So its velocity will decrease. And we have to take into account all these processes to answer the question whether the small body will remain on the surface somewhere on the surface of this car after slipping some length, some distance, or if this small body will slip off the surface of the railway car. So, the force of friction is controlled by the coefficient of friction, and the force of friction is known to be the force of normal reaction, which is mg, small m, g, that is the weight of the small body, times coefficient of friction. We know this force because this is the definition of coefficient of friction. Okay, if we know this force, then we know the acceleration of small body, because mass, small mass times its acceleration. We have two accelerations. The first of the small body, I will denote it by A1, and the second acceleration will be of the railway car. I will denote it by A2. So for the small body, the mass times its acceleration is the force, which is mgk. So acceleration of the first body is just acceleration of the free fall, coefficient of friction. We know the acceleration of the first body. And we know the acceleration in the same way. We know the acceleration of the railway car, which will be found as the same force of friction divided by the mass of the railway car, which is denoted by capital M. Again, the same second Newton's law. And F is known, small f, force of friction is known, so the acceleration will be g m coefficient of friction divided by capital M. That is the acceleration of the railway car. And we know that this acceleration is directed backward, counter the velocity, because the railway car is decelerated. I don't give you the sign here. Strictly speaking, the sign should be negative, but I give you only the magnitude of this vector, and the vector itself can be shown here so that you see the direction of this vector and its magnitude. Okay?
So the frictional force between the small body and the worker is the same as the frictional force between the worker and worker?
Sure, the same. Due to the Newton's third law, a force of action is equal to the force of reaction, equal and oppositely directed.
Okay, but the frictional force for the small body is between the body and the worker, right?
Yes, it's applied to the small body. But the same force acts on the wagon and is applied to the wagon. Yes. If I put a piece of chalk here and I will move it, there will be some force of friction acting on the piece of chalk and similar force acting on the table in different directions due to the Newton's third law. That's it, nothing more but the Newton's third law. Okay, so we know the acceleration of the small body and deceleration of the wagon. If so, we know the velocity of the small body. I will put it as v1. Everything related to the small body will have index 1. And everything related to the large body railway car will have index 2. So the velocity of the small body as a function of time will be the acceleration of the small body time, because this is a uniformly accelerated motion. The motion with constant acceleration, so the velocity is proportional to time. And the velocity of the large body of the railway car as a function of time will be equal to the initial velocity v0 minus acceleration of the large body a2 time. because the large body is decelerating. Its velocity is diminishing in time. It's becoming smaller and smaller with time. Actually, this coefficient A2 may be very small because the mass is very large standing here in denominator. So A2 may be small, but anyway, the velocity of the railway car will diminish with time. Probably it will slowly diminish, but anyway. When the body will stop, the small body will stop on the surface of the car. When the velocity of this small body will become equal to the velocity of the car. That is when v sub 1 will become equal to v sub 2. We know the velocities, and this condition defines the moment of time t when the velocities of the two bodies become equal, which means that at this particular time moment, the small body will stop sliding and will stick to the surface and move together with the surface of the car. So by equating these two expressions, we immediately find the time moment t, which will define the last moment of slipping of the small body on the surface of the car. So that will be what? Okay, I will put it this way. A1t plus A2t equals to V0, and so t from here can be found as V0 divided by A1 plus A2. A1 plus A2. Okay. V0 is given in this problem. It's the known quantity. And A1 is calculated and is given by this expression. And A2 is given by this expression. So we can, by substituting these two expressions into this formula, we will obtain what? Gk can be taken out of the round bracket, which gives us 1 plus small m divided by capital M. That's the time interval necessary for the small body to stop sliding on the surface. That's the time interval within which the small body has slipped here. And after this time moment, the small body will stick to the surface and stop sliding. Okay, that is something. That is an important step in solution of this problem. So we have found this time interval. We have found which was unknown. Originally, we did not know the time interval t. And we did not know the time interval t. But the condition, this condition, that the velocities should become equal, allows one to obtain this time interval. So now we know this time interval. And if we know the time of acceleration, actually, after the body has stopped on the surface, after it has stopped and it's stuck to the surface, then there will be no relative motion of the small body and the railway car, and there will be no forces of friction between them, and after that there will be no accelerations. So this is the time interval during which the body was moving with acceleration. And if so, we can calculate the distance covered by the small body, S1, which moved with acceleration A1 and with zero initial velocity here at this point, and acceleration, and during time interval t, the small body covered this distance. That is, the small body went from initial point to the final point, and that is the distance s. Unfortunately, we don't have time to finish this problem, but the solution is clear. We know distance s covered by a small body, and in the same way we can calculate the distance covered by the railway car from this point to this point. That will be S1 and that will be S2. And the difference between S2 and S1 must be equal to L, equal to the length of the railway car. That's the condition to find the length. This problem, if I'm not mistaken, is included in your home assignment. So we have practically discussed the solution of this problem. I have given you the clue to solution, how to solve it. Just finish it at home. I remind you that by the end of this Sunday, you're expected to send me your home assignment, your solutions of the first week. Okay, let's finish on this point.